All right, guys. So I know today is the 24th of September, and we had some issues with Zoom, and we know that screen sharing with the iPad was an issue, and some mic wasn't working for one of the students in a breakout room. So hopefully, we'll try Teams tomorrow and next Monday, and we'll see if it works better. So we're going to go ahead and start with the periodic table, and some of this stuff you have to understand. The periodic table, we could spend a month on the periodic table itself, and that's what you'll do in chemistry. You'll go over the basic concepts, and you'll deal with uh, you'll deal with the periodic table in a much more uh, detailed way in chemistry. But what we're going to do here today is we're going to go ahead and use the periodic table for our needs, and that's to understand covalent bonding and polar covalent bonding, and this idea of sharing electrons versus taking electrons. And I wasn't sure in our class video, but I'm pretty sure when I counted the electrons in the website we went to, there seemed to be an error. Uh, let's go ahead and talk about how I knew that was a problem. So when you're looking at the periodic table, there are numbers, and there's at least two different ways of numbering the periodic table. This is the more modern way, where you're dealing with one. You'll notice it starts with 1 and then ends with 18. So there's 18 columns on the periodic table. This becomes very useful, and I'll show you why in just a second. Now, the other way of numbering them would have this be 1. It still has this being 1, this being 2, but then calls this 3, 4, 5, 6, 7, and 8th column, and it takes this whole yellow section out and labels it as a transitional elements. So that's another way of numbering the periodic table. They're both very useful for different reasons. Let's go ahead and just stick with this one because that's the one we have. And if I could just beg your indulgence and ask you to just focus on the single digit here when we go over this in a second. Just worry about the ones place in this number. Ignore the tens place for a second. All right. So if this is done, if we just look at the ones place in the columns, and we're going to look at these transition metals as a completely different group of elements. Now they still follow the same rules. It's a little bit of a tweak because of the nature of their electrons and what they're doing. You'll understand what I mean when you get to chemistry as far as the transitional metals are concerned. Right now we're going to focus on the elements of life, and let's go through it and identify what those elements are. What are the elements of life? Let's first say that really you want to focus on the first four periods of the periodic table. Periods are rows, so this is period 1. This is period 1 here. This is period 2 here, so it's rows. They go this way. This is period 3. This is period 4. So it's the first 4 rows of the periodic table are where we want to focus when we're talking about life. Life on planet Earth really has to do with these first 4 rows. Again, the rows are called periods. So when you're looking at the first 4 rows of the periodic table, this is what you're talking about. Not to say that the rest of this is not important, of course. Iron, gold, osmium, all these things we will find in nature. They will be part of our food. They will be part of our water. They do impact life, but the first 4 rows are the most important to life. You will find these elements in life more involved in living systems more than you would things like uranium or francium or barium. Now, that being said, there are certain elements that are incredibly important to life, and let's go ahead and highlight what those are. Hydrogen is a big one. So when we're talking about hydrogen, here the elements of life, we're talking about hydrogen, we're talking about carbon. Carbon is incredibly important to life. In fact, it's so important that we call life on Earth carbon-based life forms. Life on Earth is considered carbon-based because it's one of the most essential elements on the periodic table for carbon. For life is carbon. But carbon, nitrogen, oxygen, so schnapps, right? Carbon, hydrogen, nitrogen, oxygen, phosphorus, sulfur. The most important elements of life. Now, obviously, there are other elements that are important. Sodium and chlorine and potassium are all involved. Calcium, magnesium. In fact, you'll probably find them in your vitamin. If you look at your vitamin pill bottle, you'll see them listed. You'll see that copper and zinc. Zinc is another one that you'll find on your vitamin bottle. So these are all important as well. Fluorine is, we put fluorine in our toothpaste. Lithium is used in numerous drugs for antidepressant. So manganese is also another one of those elements found on your, and of course iron is one of those really important ones that you'll find in our blood. It's a crucial element. So those are all important, but it's those basic elements, those elements that we're going to find over and over and over again in biomolecules and molecules that run us, that are involved in our systems. They are carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. Now, we've gone over this in the previous class, but I just want to emphasize this because I asked that question and some people weren't sure about it, and I just want to make sure that we understand. So carbon is important. Hydrogen, nitrogen, oxygen, phosphorus, and sulfur are important, and we discussed this earlier, and we said that these are really important to life, and we should make sure that we know that, and you know that for the exam because it will show up on the exam. But those elements are important. But then it comes the next question: what exactly are these things, these symbols, and what do they represent? And we figured today, when I asked those questions, there were a lot of people that weren't sure. So let's go ahead and take a look at some of this. When I see the letter C, carbon, on the periodic table, that to me means that there's an atom with 6 protons. How do I know that? I know that because of the atomic number. Now, in this particular periodic table, it doesn't give you a key, but a lot of the periodic tables will have a key. And there's this atomic number 6. The atomic number is always the smallest number in the square, and the square tile represents the element. So carbon has atomic number 6, and it has atomic mass of 12. Now, to remember what that means is that it means there's 6 protons in the nucleus of a carbon atom. Now, with 6 protons, that also means I have 6 neutrons. And how do I know that? I know that because I have an atomic mass of 12. So 6 and 6 is 12. So the nucleus of the atom looks something like that, and it's very small. and it's in the center of the atom, and almost all the mass of an atom is in the nucleus. But the electrons are what's important for biology, because what the electrons determine the chemical reactions that occur and the changes that happen, the chemical changes, the fundamental changes. If you remember from our Nearpod and previous lessons, the fundamental changes that happen in your body and all around us have to do with the electrons, not the protons and the neutrons. The protons and neutrons are fairly stable in an atom, unless there's radioactive decay, and that's a whole nother discussion. So when we're looking at protons and neutrons, they're going to be stable for any particular element. There are isotopes, there are various versions of carbon. So you can have a carbon, you have carbon 12, you could have carbon 14. But carbon 14 also has 6 protons. All carbons have 6 protons. The difference then is in the number of neutrons, how many N's there are. And we'll get back to that later. However, it's just really important that you understand that when we're talking about biology, what we're really worried about, for the most part, is the electrons. The number of neutrons are and protons are pretty stable. So it turns out that there are these general areas around the atom that we call orbitals, and they actually are representing a region of space around the nucleus. That region of space, and I call it a region because it's not a path the way you might think, like a satellite goes around the Earth. We do draw it that way in a sense, the way I just drew it. I drew that. But it's different in the sense that these are not distinct and predictable paths. In fact, they're just regions of probability. And I know you don't understand that, but just try not to think of this as a satellite going around the planet per se. There is a distance between the nucleus and this line here, this orbital, we'll call it an orbital, that suggests that there's a certain number of electrons that tend to be found in this space. And in general, the first space, the first orbital, orbital 1, the first orbital, the first shell, and it's a shell defines this space with a level of probability you're going to find electrons. That those electrons' path are called orbitals within the shell. So if you can think of a shell like an onion, if you think of an onion, you have many layers to an onion, or like a Russian nesting doll, one inside the other. So too are these shells, and the very first shell, being the closest to the nucleus, has 2 electrons in it, the maximum of 2 electrons. The electrons have a negative charge, so I'm putting a little line. You'll notice that the protons have a positive charge, and I put a little plus. The neutrons are neutral. I know N also the word negative also begins with N, but neutral means 0 charge. I almost wish they would have called the neutron zilch. It would make life easier for me, but in any case. 2 electrons are the maximum number of electrons that shell can hold. And why is that? Because these 2 electrons are both negative. What do they do to each other? What do 2 negative things do to one another? What do 2 like charges do to one another? Well, I hope you said repel. They push each other away. The protons push each other away, but there's a strong force that's holding them together. The electrons are pushing each other away. The only thing that's pulling them close is pulling them in and holding them into this space, this probability area called a shell, and into their paths called orbitals, the only thing that's holding them there is the pull from the protons. So the strength, this number of protons is 6, is the only thing that's holding the electrons there. So if there's 6 positive charges, how many electrons would you expect to see in carbon? Well, I hope you said 6. So there's 2 here, and so you'd expect to see 4 more. Well, the next shell is called the second shell. And there's 2, this second shell. That also has an orbital that can hold 2 electrons. So 1 there, 1 there. But it also has a second orbital called the p orbital that can hold 6 more electrons. So the second shell can hold up to 8 electrons. So from the second all the way forward, from shell 2 to shell 5, 6, shell 2 to shell 3, 4, 5, 6, 7, from then on, all the shells can hold 8 electrons. Only the first shell has that limit of 2. That's why we call and that valence shell, valence is called the outer shell, and generally this, how many electrons fit into it, is the number 8. So we call it the octet rule, right? Because you expect there to be 8 in the outer shell, except for that first shell, which is, it's going to be one of those things you're going to have to remember there's an exception there. So this exception, this first shell only has 2 electrons. We'll come up in a minute, especially when we're talking about hydrogen. All right, so hydrogen is the only one you see. There's only 2 elements in the first shell. The first shell is also represented by the first period. These shells fill in from left to right, from top to bottom as we move forward. The electrons fill up, and you'll see that as you go on and study chemistry later. I'm trying to summarize this as quickly as I can without having to go into too much detail, but I have to balance that with explaining the material so that you understand it. The best way would be for me to go ahead and explain the material in detail and then walk you up through the content, but that would take too long. So we have the first shell holds 2 electrons. We'll go back to that and we'll see how that impacts this bonding arrangement later. But from now on, from the second shell on, it can hold up to 8 electrons. So that's that octet rule. Now, as you move up, as you keep adding electrons, you always start with the first shell and then move outward. Always start in and then move out. That's how they fill in. The first 2 fill in here. The next 2 sit out here in the second shell because they repel. These electrons all repel each other in 3-dimensional space. I hope that makes sense, that these are repelling each other in 3-dimensional space because the negative like charges repel. So this accounts for 4 electrons, 1, 2, 3, 4. But we said carbon has 6 protons. So how many electrons would you expect to be around carbon? We've already said we expect 6. Right now we only have 4. So we need 2 more electrons. So there's another one, and there's another one. So now we have 1, 2, 3, 4, 5, 6 electrons. And we have 6 protons. I drew them, and you see the number here. So 6 minus 6 is 0. So this is the neutral form. The neutral form of the atom. Well, that's great, except we have a second rule that we talked about. We have a second rule, so that takes care of rule 1. Elements tend to move towards neutrality. They tend to be more stable when there's no charge. So this atom is more stable than it would if it had a charge. But the second rule is they tend to move towards getting a full valence shell. A full valence shell. Now, for the most part, for most of these atoms on this periodic table, the full valence shell means 8. Because as you see here with carbon, there's 1, 2, 3, 4. It could fit 8, so it needs 4 more. All right. But these two rules drive how elements bond. The fact that they tend towards neutrality and that full valence shell. So remember those two rules as we move forward, but those are indeed the rules that we have to make sure you know, because you're going to see them applied over and over and over again. That octet rule. All right, so that's carbon. Let's keep that here. And let's put that off to the side. And let's change it. What happens if we were dealing with chlorine? So with carbon, I expect to see 4 there. Now, what about chlorine? How many electrons are in chlorine? Now, we talked about it in class, and we said the chlorine atom. We're going to go and just not even erase the 4 that we did with carbon. We see the chlorine atom sits here. It's number 17. It has 35 atomic mass. We're not concerned with the neutrons, really. We just know they have 17. So here I would expect to see 17. So if I look at chlorine, I expect in its chlorine 17. I always put this little dash in the 7 to distinguish it from the 1, the number 1. So don't get confused. This is a 7. So that's 17. So I got I expect to see 17 chlorine atoms, electrons around the atom. 17 protons here. So if I zoomed in, I wonder if I can, if I zoomed in, here we have 6, because we drew carbons. So if I wanted to make chlorine, I'd add 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17. And then I know I have 35 atomic mass, so I would go ahead and add another so many. I'd go ahead and add so many neutrons, but the neutrons really are not my concern right now. I just wanted to make sure you understood there's 17 protons sitting in the middle of this atom, and since there's 17 protons, I'd expect to see 17 electrons. So right now I have 6 electrons, so I'm going to go ahead and keep adding. 4, 5, 6, 7, 8. So that's 8, right? 9, 10. So I got 10. And don't forget the 2 that are in the first shell. So I have 10. I need 7 more. So I go ahead and draw an outer shell again. And actually, I had these sitting here for this reason. So I go ahead and add another shell. Again, the distance between the shells is determined by the repulsion of the electrons, right? So this is the third shell. Now again, the third shell can hold 8. So I'll go ahead and draw them. There's 1, 2. So right now I have 12, right? I have the 8 here, 9, 10. 11, 12, so I have 12, 13, 14, 15, 16, 17, so that's it. I have 17 electrons. And that's why I had a problem with what I looked at when I looked at the video, at the website we looked at together in the class video. I only counted 16. There should have been 17. There should have been 17 electrons. Why should maybe they didn't show the first shell, maybe there was something else going on, but from what I counted, I only counted 16. There should have been 17 electrons, not 16. So in any case, chlorine has a full shell, for it to be neutral, for it not to have any charge, chlorine would have to have 17 electrons. And it would look something like this. But notice its outer shell would have how many? 2, 1, 2, 3, 4, 5, 6, 7. It would have 7 in its outer shell. And carbon, having 6 total electrons, would have how many in its outer shell? It would have 1, 2, 3, 4. Now let's take a look at those numbers I told you to keep an eye on. The ones place and the columns number. Carbon is in the 14th column, but the ones place is 4. And the 4 represents the 4 electrons in the valence shell. If you look at chlorine, chlorine is in group 17 or 7, and we'd expect to see 7 electrons in the outer shell, and we do, indeed we do. So these numbers, the ones place, tells you how many electrons are in the outer shell, in the valence, except for these. These are odd, which is why I tell you that they're different. We call them transition elements. We're not going to really get into the chemistry of these. And when I say chemistry, I mean the movement of these electrons is really what chemistry is all about. We're gonna just try not to involve this group of elements at all for right now, and just worry about these over here. And so, how many valence electrons would I expect to see in any of these elements? I'd expect to see 1 valence electron. I expect to see 2 valence electrons. I expect to see 3. If they're neutral, if the atom is neutral, I expect to see 1 or 2 or 3 or 4 or 5. Where am I getting these numbers? The ones place. All right, so I just count the columns. 1, 2, 3, 4, 5, 6, 7, and 8. From 1 to 8, not including the center, tells me how many electrons are in all the atoms in that column. So it's going to make your life a lot easier if you understand that. All right. So that's carbon and that's chlorine, and that's why I knew there was something wrong with what we were looking at on the website that we looked at. Oxygen, and instead of drawing out all those electrons, all those protons, I can just look at oxygen, and I know that oxygen. So when we look at oxygen again, there's number 8, so it tells me 8 protons, but it's in group 6. You see 6, so I know it has 8 protons, but I know it has 6. When it's neutral, it has 6 in the outer shell. So I don't have to worry about all that. All I have to do is put oxygen, and I know I can draw an outer shell, draw one single circle. Let me go ahead and draw yellow to keep it together, the same as before. So there's my oxygen. I'm just going to put O for oxygen instead of trying to draw out the entire thing. I'll just take a valence shell, single valence shell, and put oxygen, O for oxygen. All right. Oxygen has how many in the outer shell? This is the valence shell. It's only 6, so I can go ahead and put 6 electrons in the outer shell. So the 1, 2, 3, 4, 5, 6. And I said when the atom is neutral, there are 6. That's what that number means. So when the atom is neutral, there are 6. So remember our 2 rules. Atoms tend to move towards neutrality, right? Neutrality. To be stable, right? And the second is atoms tend to want a full valence shell, so they move towards, I hate to use that word want, they tend to move towards a full valence shell. The valence shell is represented by the circle I just drew. There's 6 of them in there. How many would I expect to see in there? Well, it's not the first shell, because if it was the first shell, there would only be 2. So I expect to see 8, the octet rule. So I have 6, I expect to see 8. Well, how many are missing then? I'm missing 1, 2. There's 2 spaces. So I need to have 2 in order to get that full outer shell. How am I going to get those 2? Well, let's assume that this thing's just floating around space. These oxygen atoms are floating around space, and they come across maybe another hydrogen, another atom called hydrogen. Well, hydrogen's in the first column, so it also has a valence shell. Let's make sure we understand that. Oxygen has a valence shell. It has one electron in its outer shell. It needs how many? How many does it want? Now, if you follow the octet rule, you'd say 8. Except that if you paid attention, what I said earlier, hydrogen's an exception. It's in the first row. It only needs 2 electrons because the first shell only needs 2. And this is the first shell. How do I know it's the first shell? Because it's in this row, you see. It's in this row. So this is 1 electron in the outer shell. And if I take it, though, and I move it here, and I say, what if there's 2 of them? So now there's 2 hydrogens, floating, running around in space, bumping into each other. How do we get an extra? It needs 2, only has 1. This one needs 2, only has 1. This one needs 2 more electrons. It only has 6, needs 8. How are you going to get both of these satisfied? In other words, keeping them neutral. If I add an electron, it's going to make this thing negative, right? +1 minus 2 is -1, so it'd have a -1 charge. If I added 2 electrons here, it would be +8 minus 10, so it'd have a -2 charge, right? You can do the math. So how do I get these to be neutral and have a full outer shell? They share electrons. And so if we shared electrons, if this electron was shared between the 2 of them, that they shared this pair of electrons were shared, now all of a sudden this one here gets 6, these 6 that it has already, plus it gets to share this extra one so that it has 7. It used to have 6 and it has an extra one. It's sharing. Because remember, sharing means that this oxygen gets this one and this one. When you share something, and I know some kids have a bad idea what sharing is. If I have a house, I own a house. My wife is my partner. She shares the house with me. That means the house belongs to her and to me. If somebody asks who owns the house, well, both of us do. I own it and she owns it. She doesn't have half and I have half. That's not how it works. We both own it. So when we look at these electrons, this hydrogen has this electron and this one, and this oxygen has this electron and this one. So they're sharing. So that's bond. That's a bond. That's called a bond. That's what a covalent bond is a sharing of electrons. And of course, oxygen still needs another one, so it would go ahead and share with 2 different hydrogens in this case. Would share another set of electrons there. And so oxygen then would form 2 bonds, and hydrogen forms 1 bond. Why? Because this is how you get both neutral, how you can have an atom that's both neutral and have a full outer shell. Now we draw it differently because there's 2 lone pairs of electrons and they repel each other, and we have because when we start to take into account all the repulsion and attractions that are going on, what we find is that hydrogen, the most stable form, and I'm going to draw it a different way. I'm not going to draw the circles at all. I'm just going to go ahead and draw oxygen, O for oxygen. I'm going to draw a line for the bond, another line for the bond. I'm going to draw this one time. I'm going to draw the lone pair of electrons here, because notice that there is 1, 2, 3, 4 electrons that are not used in bonding. For various reasons you'll learn in chemistry, they are still there and they stick together in pairs. And what we have here is the symbol that we like to draw, the water molecule as we'd like to draw it. Now this can become important in just a minute. So when we look at that, that's a water molecule. Also, another way of drawing this out would be H2O, why H2O? The lowercase, the subscript 2 represents the fact that there's two of them. The O is obviously the oxygen, the H the hydrogen. So these are sharing, but just so the electrons in this bond, and you have to remember that what's a line? It's a connection between 2 points. So each of these, think of when you see the line, think of the 2 points at the end. There's 2 electrons. They're being shared, but unlike a marriage where things are shared evenly, this is more like a big brother sharing with a little brother. Big brother is stronger, tends to want to keep the stuff that it's sharing more than the little brother. He's stronger, and the word that we use that you'll hear in videos and read in books is called electronegativity. And it's a word that just is, the only thing it really is representing is the strength of the atoms, or the atom's ability, the element's ability to attract electrons. And oxygen is much stronger, is much better at it than hydrogen. And so what you get is you get a partial, and this is the symbol delta. Symbol delta. It's a Greek letter. And it's the lowercase of this symbol, which is also delta. So this is capital delta. Means change, but the lowercase delta in this case means partial. So it's a partial negative charge. And let me go ahead and draw it in red instead of yellow. It's a partial negative charge. Over here is a partial negative charge from this bond, and of course these become partially positive charge. Now, why do I say partial? It's because they're sharing unevenly. So there's just a slight negative charge sometimes when the oxygen has the electrons more often than the hydrogen, and this one slightly loses it a little more often. So it's big brother versus little brother. This one has the electrons a little more often, so they have a larger share of the negative charge. So because they're sharing unevenly, and because they have two sides, we call these poles. So they're dipole forces. These are polar bonds. Polar means two sides. And this molecule is polar. This is going to be extremely important as we move on. So it's really important you understand that water is polar. So make sure you get that. Water is polar. Water is the example of polarity. So it's a bond that is definitely polar. Now you could get that oxygen, instead of meeting up with two hydrogens, maybe that oxygen meets up with another oxygen. And just drawing the dots without drawing the circles, right? Just drawing the dots. You have an oxygen meeting up with another oxygen, and just drawing the dots, we know that there's oxygen is atomic number of 8 with its valence shell of 6. So how do I know there's 6? Because I look at the column number, the ones place. I know there's 6. So 1, 2, 3, 4, 5, 6. And I know there's 1, 2, 3, 4, 5, 6. So there's 6 in each. I know that. So now how are we going to share? Well, how do you get 8 if there's just oxygen involved? Well, the way you're going to share is you're going to get the electrons to share this way. Let me draw it in red so that you don't confuse the dots with the electrons. So this sharing is going to happen around these two are going to share, and these two are going to share. So what's going to end up happening is you're going to end up with a double bond. So you're going to have an oxygen and an oxygen that's going to share two bonds. Now, oxygen and oxygen are equally strong. They're two brothers of the same age, or sisters of the same age, so they're going to share evenly. They'll make sure of it. They're both equally strong. So this is an example of a nonpolar bond. Nonpolar bond, which means that there is no partial negative charge or partial positive charge. Now I'm going to leave the reasons why this is important for later, but it is very important that you understand this. So let's make sure we get that and make sure you understand that this is the difference between polar bond and nonpolar bond is going to be incredibly important coming up, and will be pretty much definitive on a lot of the different processes that we're going to talk about later. So when we talk about water going from the roots to the top of the trees, it's because of these polar bonds. When we talk about why is the boiling point of materials, the freezing point of materials, all this is due to this polarity versus polar versus nonpolar molecules. So it's important that you understand this idea of polarity. It's important you understand that nonpolar means that these molecules share evenly and have no charge at all, where these have partial charges. So make sure you get that straight and you understand that. And I think that's going to be all we're going to need to do for now. And I'm at 40 minutes instead of 20 minutes, so I'm sorry about that, but I just think it's better that I explain it rather than leaving it halfway unexplained just to meet that 20-minute mark. All right, have a good one. Bye-bye.